still not working, I'll be using the highlight laser pointer. So probably if based on this, I'll show you all those things. Okay, so tomorrow or probably the next class, because Saturday is working for us. So Saturday I'll be probably my pen will be working on that day. Okay, anyways, so this is going to be our third lecture, and today we are going to see more of a structure of power systems, how actually power systems look like. This is again very elementary, I'm sure everybody knows it, but just to give a recap on this. So basically, everybody knows that power system is huge. It's a big structure with lot of components, lot of equipments at different location, which connects everything and perfectly works uh, till any disturbance or contingency takes place. So the basic characteristics of very fundamental characteristics of power systems is either it has to have a three-phase AC system, and this is the way we all. If you maybe the frequency of voltage may be different across the countries, but it will always be a three-phase AC system. And recently, people have started talking about going back to the DC systems. I'm sure everybody has anyway we have HVDCs. HVDC is the high voltage DC systems, that is we have anyway, but because of the cost of the inverter and converter, HVDCs are generally deployed for basically long kilometers. If the kilometer of those HVDC lines is beyond a particular threshold, then only we deploy HVDC lines. But this is for the high voltage. But now people are talking about the DC systems in low voltage as well. So low voltage as well means, like, obviously we have these days we are talking about solars, we are talking about electric vehicles, we are talking about batteries, energy storage devices, fuel cells. So these devices, they or these energy sources, they generate electricity in DC, they do not generate in AC. So obviously if we have a converter, let's obviously all of our appliances are works in AC system, right? They are not designed to work on DC system. So what happens is, if they generate energies, these small DC sources, if they generate energy in DC, and then to utilize those energy we need to convert it into AC and then utilize it in AC. Now the problem here is, because that conversion from DC to AC, that might be that might create loss in the energy. It will obviously, there will be some loss, it cannot be 100% efficient that there will be no loss for conversion from DC to AC. So that's why people are talking about these days DC networks, and for the smaller scale, even people are developing some appliances, some necessary appliances which can be directly be connected to these DC energy sources. So that is anyway happening in the very low voltage level, but HVDC is anyway. But basic structure in broad sense, it is always AC systems, three-phase AC systems, which is operating at a constant voltage. Constant voltage can be at because we have transformers, so every voltage, there can be different voltage levels, but at different voltage levels the voltage has to be constant at a particular value, and obviously there will be a frequency as well. So this is the basic structure, and here we connect all our generation and transmission facilities in three phase. Also we have industrial loads, like for big industrial loads like car manufacturing industry, cement industry, this iron ore industries, all the big industries you can think of. All these industrial loads are mostly three phase. Not mostly, it is always three phase, because they have they the motors, the pumps, the heaters, everything what they are using, they all take three phase power. So that's why it's always three phase loads. And in residential and commercial loads, There can be single phase or three phase. It depends on the availability as well as the choice of the user. So I'm not sure if you have observed at your home, is it single phase or three phase? Because in residential areas, people are means in India, I'm sure people in many states, state electricity board is offering three phase supply. So it is not like three phase will be utilized, it will be single phase only. But what happens is, let's say you have three different rooms, one, let's say one drawing room, one bedroom, and one another bedroom. So what you can do, you can connect one drawing room with one phase, one bedroom with another phase, and another bedroom with another phase. So this way you can balance out all the three phases and you can distribute the three phases. So this is the way many state electricity board is offering that feature, as well as people are also using those three phase. The advantage is obviously, if you have a single phase, if you increase the load at your home, the voltage keeps on dropping, and then you see flickers, you also see the voltage dip. And even if you just have a single phase, what will happen on the upstream of that single phase, there might be some load changes happening, because of which your voltage and frequency, whatever you are getting at your home, will also get affected. So that is the logic why people go for three phase. But the underlining is that it's your choice or the user's choice to go for residential single phase or three phase in residential and commercial sectors. Another important point is we want all these three phase, either it is industrial load, residential load, commercial load, whatever is the connection, we want all these three phase system to be balanced. Why do we want our three phase system to be balanced? Can anybody answer this? Why do we want our three phase system to be balanced?
I think um, I think it will affect on the stability of loads. There will be fluctuation in voltage and current,
No,
and that will damage our
no, stability,
component outdoors.
stability is a different thing. Stability gets affected when the disturbances, let's say a big disturbance takes place, then gradually the system will get affected and it may go out of synchronism, or it can go on become unstable. But it is not only stability. Stability comes afterward. Before that, there is also one more thing which can get affected. But yes, stability is one factor, but that is much later actually.
Quality.
Quality, yes, part of it, yes, quality can also get
Or
affected.
system quality.
Quality of voltage, right? Quality of voltage and frequency. Or quality in what sense you were talking about?
voltage, sir. When
Huh?
the load not balancing, we will the start point will shift it. Then there is different voltage on each phase. We will
Okay.
get different voltage.
Agreed, agreed. There will be different voltage in three phases. That's why we call it as unbalanced. I agree. But what is the issue? Why we want it to be balanced? What is the problem if we run on three different voltages or unbalanced system?
Sir, if
Current,
there will be circulating currents if there is an unbalance in the phases or anything, three phases.
Yes, it is actually circulating current, or because we have a star connection at the generator side, there will be current flowing in the neutral wire, and those excess current, because those excess currents are generated because of the generator movement. So if you are generating additional currents, and energy is very we have to use energy efficiently, so additional currents will flow through this neutral wire, and it will flow through ground, and there will be a circulating current across appliances, and this additional current will lead to losses. It will not be utilized for any task. So that is the main reason why we want it to be balanced. I agree that stability is an issue, quality as in is definitely an issue. Different voltages will be there, different current will be there. I agree on all these 3 points, but only thing is that it has to avoid that circulating current. We do not want any current to flow on the neutral, right? If it is flowing, then it is just waste of current, right? Waste of energy, because that is not going to be utilized in any of the appliances or equipment. That's why we want our system to be balanced. This is one part from the operational point of view or from the technical point of view. Another important point why we want our system to be balanced is from the mathematics point of view, mathematics or the solution point of view. If the system is unbalanced, frankly, I'm sure you must have studied Newton-Raphson load flow, Gauss-Seidel load flow, the basic load flow or power flow, which you must have studied in your bachelor's. Those load flow algorithms, they assume all the mathematics in power system, they actually assume the system is balanced. Even if you talk about the stability studies, even in the stability studies system, it is assumed that the system is balanced. Then only you go ahead with the studies. So simple issue, what will happen, the calculation or solution methods for three-phase system, whatever we have developed in past decades, past 20 years, 30 years, all those methods will need to be revisited or revised, because all those methods, the primary assumption is that the system is always balanced. If it is unbalanced, then those methods will not work, or you need to do some changes to make that methods work. Okay, so that is the another problem what happens if you have unbalanced system. But anyways, there are methods which can be done for solving this unbalanced three-phase system. I'm sure many of you must have taken the course distribution system analysis. There you might be seeing, because distribution system are often unbalanced, so therefore you may there will be a topic where you will be seeing about power flow, unbalanced power flow. Okay, now another important characteristics, basic characteristics, that the synchronous machines are always used for generation. All the machines for generating electricity are synchronous machine. Machine means all the rotating machine. Now there is a catch here. There is one machine which is not synchronous, which is actually induction machine. Can you name which generation source is actually not synchronous?
Wind turbine.
Perfect, perfect, very good, very good. So wind turbine is not a synchronous machine, it is an induction machine, and that is the only rotating machine where we use non-synchronous or induction machine. Rest all machines are synchronous machine. The basic idea is that because if it is a varying, because for synchronous machine you need a constant speed for rotating that rotor. If the speed is not constant, then it is preferable to go for induction machines. Perfect, perfect, very good. So, and also the transmission network is classified into transmission system, sub-transmission system, and distribution system, where transmission system is often high voltage systems. Distribution system is often the low voltage systems, where the operator also changes, because an operator only controls either the transmission or distribution, but it does not control both, because obviously for an operator point of view, controlling a big system becomes really difficult. So there are generally two different operators who takes care of transmission and distribution, and in between transmission and distribution there is often an interconnection few of the transmission line that comes under sub transmission system, and this sub transmission system can either be either be operated by transmission and or distribution. It depends on situation to situation. Let us see exactly where transmission and distribution takes place. So if you see this diagram on the left, on the right, here the topmost is a transmission system, where you can see all the high voltage lines are there, big generators. Just a second, now I'm getting a call. Just a second. Just a second. So I was telling you about here that in the diagram on the right, the top is the transmission system where it is all high voltage lines, as well as transformers and generators are there. And below there is a sub transmission, and below that it is a distribution systems. So let me just complete transmission and distribution, then come to the sub transmission, because it is just the intermediate one. It is not necessary that always there is a sub transmission network available in a power systems. It is just a in between connection. At times it is not there, because if sub transmission is controlled by transmission, so we call this complete part as a transmission. Only just the naming changes, but it is still controlled by transmission, so we call it transmission. Or if this is sub transmission is controlled by distribution operator, then it is again part of a distribution operator. So it is just an intermediate one. There's nothing to complicate it here. Now, from the distribution system point of view, here you have generally the low voltage systems, and all the loads. Loads means residential load, commercial loads, and the industrial loads are often connected, or always connected in distribution system. Only to differentiate this sub transmission, there might be some industrial loads which can directly connect to this sub transmission systems. There can be, because let's say there are big industries, for example, let's say car manufacturing industry, or cement industry, or this iron ore bauxite industries, or let's say a lot of you can think of many industries like like for our regular day-to-day needs, there are a lot of industries, like even food manufacturing industries. So those industries, they require intensive amount of power, and for that they generally prefer connecting themselves to the higher voltage levels. Why? Because the reason is, it depends on the, let's say if we talk about car manufacturing industries, there they use big size motors. Motors are used which is really big in size. Big in size means in terms of voltage level and the power what they consume. So those generator or those motors, they if they have those type of motors, they prefer to connect directly to the sub transmission system. So yeah, so that way you can say a bit of difference is there, but overall this is depends on the who controls it. Now, from the primary equipment point of view, there are obviously, you can see here, there are transmission lines and distribution lines in a power system. You have a substation. So all the horizontal lines, the bold horizontal lines, what you are seeing, these lines are often a substation. These lines are often a substation. For example, if I tell you that there is a transformer here, so that means if a transformer is here, that means this both the lines are going to be in one substation. They are not going to be in two different substations. That is, and if there is just line connecting between two, we call them as buses. So two buses, then there will be two different substations. Now for this line, let's say if you see from the top, this horizontal line, this bus, because one is connected, there are two transformers. One transformer is connecting a generator and one transformer is connecting a load. Here there can be a situation that both the transformers are connected in one substation, but generator is located far away and load is also located far away, but they are connected by wires obviously. But these transformers can be in the substation here at the transmission in this bus, or this transformer can be there at the generator location or at the load location. It depends how a designer or the planning has been done for these lines. So obviously in substation you will see transformers, breakers, disconnectors, bus bars. Those will be there inside the substation. There will be many more equipments, but just to name few. And there will be very many control devices, one shunt capacitors, reactors, fact devices, tap changers, phase shifting transformers. These are the control devices. So I'm sure everybody knows how these some basic idea you must have how these devices control uh, and which parameter they actually control. So like for example, the shunt capacitors and reactors, they affect directly the voltage wherever they are connected. Fact devices, they again directly affects the voltages wherever they are connected. Tap changers, they again affect the voltages wherever they are connected. These tap changers are nothing but the transformers. So you change the tap of the transformer and the voltages can be step up or step down depending on the situation. Now this phase shifting transformer, this he, as by the name you can think of that phase shifting. Phase shifting means voltage has two components in a power system. Voltage has a magnet, because voltage is a complex quantity. So then there is a voltage magnitude and there is an angle. So all these three on top, shunt capacitors, reactors, fact devices, and tap changers, they affect the voltage magnitude. But this phase shifting transformer, they actually affect the phase shifting voltage angle. So this is the difference. This is the part which they affect. So they affect the voltage angle, not the voltage magnitude. So yeah, just wanted to give you a heads up on this. And lastly, you will see in the substation because we want to measure a lot of informations across the network, we want the data to be transferred at the control center, where the control center or the engineer sitting at a control center can take decisions based on the data which is coming up. So those data are generally means measured by, there are measurement transformers which actually, because obviously let's say for example, if let's say you see this 110 kV, this line, so this line, the current will be flowing, will be around 500 600 ampere currents will be flowing. Obviously no measuring device can actually measure that 500 600 ampere directly. So you have measurement transformers, which is known as CTPT, current transformers and potential transformer, which is stepped down to a normal value or nominal value, and there you connect all these measuring devices which actually measures the value of voltage and current, and then you transmit that data. So this is the basic idea how a power system looks like. Now, just to give you again an idea, broadly you see generators, transmission systems, distribution system, and small consumers can be connected to a distribution system, or as I said, the large consumers can be directly be connected to a transmission system depending on their requirement and the voltage level connections. Now this type of system we used to see before the liberalization, or I would say restructuring, or a simple sense deregulation of power system. Deregulation means basically we unbundled the system, we unbundled the organizations of generations, we unbundled the organization of transmission systems, and we unbundled the distribution system. So we separated all these three from a single entity. This, after these transformations, you see that there are new generations which are coming up, like small generators like solar, wind, batteries, EVs. These earlier days we were not allowed to generate at this level and to inject power at the transmission side. It is always a unidirectional. Only generators will generate and they will supply power to the transmission system, and transmission system will supply power to the distribution systems, or through for small consumers or directly to the large consumers. But after the basically new technologies where small power sources can be directly be connected at the consumer level, then these generators are actually known as distributed generators, because they are very small generators and distributed across the areas. So therefore we call them as distributed generators, and these can be connected, and then these can actually inject power to the transmission systems, and whatever they inject, they get money for it. So these economics as well as the new technology for the small generators, which becomes viable for the small consumers to install those. This is the advantages what we have seen with the transformation, what I was talking about, either deregulation, or you call it as deregulation, restructuring, or in a simple sense you can also say it as liberalization. So and here also even the large consumers, for example, I don't know if you know this or not, in most of the aluminum or the bauxite ore industries, they have their own generators installed at their plant location. So what they do, that because the bauxite ore industry, they require immense amount of power, and even the cement industries also. So what they do, that they have a small generator connected at their location also. So if at night time, or let's say if the shift is changing, because the workers work there in shifts, if the shifts are changing, then these generators during that time of shift or night time, when the plant is closed, that time you does not need more power, only you might be needing only the lighting load and the few essential services which are working. So in that case you can directly run your own generator and consume your own power instead of taking from the transmission system. It depends again on the prices, because the price from whatever electricity price they are getting from the transmission system, and whatever price they are incurring because of the running of its own generator, if whichever is cheaper, obviously as a consumer you will prefer that to work on. So these transformations have happened during the past, and we will see those transformations in detail in just coming up slides. So initially, the structure of power systems, as I told you here, it was vertically integrated. We call it the exact term before the liberalization or restructuring or deregulation, whatever name you call it. It was known as vertically integrated utility. And vertically integrated means everything: generation, transmission and distribution, all these three comes under one organization. So this blue line, what does this blue line mean, is that all these three segments of power system, generation systems, transmission systems and distribution systems, all three was operated by a single entity. Often those entity was government, because it was, I'm talking the earlier days of power systems. Obviously government wanted to initiate that more people use electricity, so initiation always happened from the government side, and it was a huge investment thing, so obviously government can only afford it. So the government used to take care of everything in a broad sense, and there was a regulator. This regulator's role was just to ensure that whatever operation is happening, or just to keep a cross check on the government, that whatever is happening is happening with a proper rule, and the prices what this vertically integrated utility is offering to the small consumers or the large consumers, it is fair. So just to see them in detail, vertically integrated utilities, basically that's what I said, it covers the whole chain of power production, transmission and distribution, and finally delivery also. And it determines the price of electricity, obviously subject to the approval of by regulator. And regulator, the role of regulator is generally to check the prices, as well as create the rules of procedures for further investments, operation, everything, control, everything was taken care by the regulator. Means regulator is the just by the name, it regulates or it gives the rules for doing all the operations of power systems. Now, as I said, that there was liberalization, and after the liberalizations, lot of has changed. So let us see the liberalized electricity systems. Now here you can see from the diagram that that there is one regulator that was there previously. There is a new entity which came, which is known as trader. There are many generation companies which came into existence. This can be either owned by government, private, or even with the individual, with a small scale individual owners. And there is this transmission system where this system can be operated by either by TSO or ISO. TSO is transmission system operator. ISO is an independent system operator. Just for the timing, just assume that it is a system operator. I'll tell you later on what is the meaning of this TSO and ISO, how do we differentiate it. So let us see system operator. And then distribution companies are formed. Basically earlier all the things were in one, now different distribution companies came into existence, and obviously the large consumer where their distributed generation is also there, and there are small consumers are also there. Now can you tell me what is the role of a regulator in the liberalized electricity systems? Can anybody just guess? And frankly, this is the way we are working currently in India, in Europe, in US, everywhere. This is the current way we are working power system as.
Balancing between loads and generating?
Balancing role is with system operator, not with the regulator. Regulator roles remains the same. It ensures the fairness in the operation of power system. It ensures the prices. It ensures the calculation, or not the prices. It ensures the calculation of prices. The method is fair to everyone, all these stakeholders. So it ensures the fair and sustainable environment for electricity market to work, or rather power system to work. This is the main role of the regulator. Right. Now, can anybody guess what is the role of the trader here?
Exchange of electricity between different companies.
Exchange, exactly what do you mean by exchange here?
Purchasing power from one company and then supplying to the other.
Perfect. Means even if you go by the basic English meaning of trader, exactly that is the thing where trader, actually trader means it is like who is trading the power, because we have only one commodity or one product, which is power. It is buying and selling, or rather you can say it is providing a platform to do buying and selling. So it actually does not own any physical asset. He does not own any generation company. He does not own any transmission system. He does not own any distribution system. He just do the trading part and provide different financial services. So there are different financial services which is required for power systems, but the product in overall is always power. And also to maintain the voltage and frequency to a nominal value, but it is always it requires different services to, and different time interval the services requires differently. So therefore this in detail we are going to see in the next semester in our deregulation course, but whoever teaches it, either me or anyone else, but you will be able to see more detail there. Now generation companies, They can be of government. They can be they own actually a power plant of any type, either coal, diesel, gas, renewable, hydro, nuclear, whatever it is. They own that generator type, and they operate the power plants, not just the power plants, not the complete power system, just the power plants they operate. So they own the power plants and they operate the power plants. Now, system operator. So let me just can anybody guess? One of you has said already that it actually ensures the balancing of the power system. Also, it ensures the security of the system. So what exactly here I want to take a pause and tell you about this system operator. System operator is basically a person who owns the transmission system and operates the this transmission system, because generator generates power, distribution companies, you can say, or the small consumers or the large consumers, you can say, they consume power. So this transmission system is kind of a connection or a bridge between the generation companies and distribution companies. So generally these transmission systems are owned by let's say in Indian context, if I say Power Grid Corporation of India, they own the transmission system. And earlier, now things have changed, but earlier Power Grid Corporation of India used to control or manage this transmission system, because all the manage means in terms of balancing, in terms of security, in terms of voltages, everything has to be taken care by the same entity, and that same entity used to be Power Grid in India. And whenever you have the transmission system and the operator, the system operator, both is owned or controlled by single entity, you call it as a TSO. TSO is transmission system operator. So transmission system operator is the person who owns the transmission system. Also, he controls the power system or operates the power system. So then you call it as TSO. Now what happened is, because the development of or the installation of these transmission lines were also privatized. I told in the previous lecture that after a particular act, they also privatized the transmission systems. Now when you have private players participating in participating in installing the transmission systems, you have created a conflict of interest, because as an operator I will prefer the power flowing over the transmission lines which are installed by a government, and then compared to the private players. So therefore the prices of installing those lines also differ. So therefore what they did is they divided the companies. Means they separated the companies. The transmission system is owned by a different entity and the system operator is a different entity. Whenever this happened, it is known as, in this case, the system operator known as ISO, independent system operator. ISO full form is independent system operator. So it does not get influenced by any other factor. And whenever this ISO is separated from the transmission system, then the transmission system or the owner of the transmission system is actually known as CTU, Central Transmission Utility. So this CTU is mostly in India is Power Grid, but there are many private players who are also part of CTU, or they are separate CTUs who are taking care of the lines which they have installed. So this is the difference. But eventually the system operator role is always the same. Either if it is TSO or ISO, it always operates the power systems to ensure the balance between generation and demand, as well as ensure that the voltages and frequency are set at a nominal value. And also security and everything is taken care of by the system operator. So system operator is the man or the entity who is running the show. So it is the simple logic. It's simple to, like a magician shows the magic, and he is the one-man army for the show. He ensures that everything is working properly. The same way system operator runs the show for the power system across in every country. And lastly, distribution company is there. This is very simple. Everybody knows that it operates the distribution grid, and it supplies the power to the consumers. And the role of distribution company is mostly to collect the electricity charges or the electricity bills. All the collection is done by the distribution companies, and then these distribution company pass on the money to the system operator, and then system operator pass on that money to the generators for their generation. So this is the way they generally happens. This process happens. Right, everything is fine as of now. Any queries? Yes, please. No queries? Okay, so let us move to the next slide. So now, obviously, when we say that the power systems are there, but now people wanted more power systems to be more secure. And the idea of securing more power is to connect different power systems. And when you connect different power systems, it becomes more easy to operate, and it becomes smooth in process. It provides security, it provides reliability, it provides economical power. Lot of factors you can add onto interconnections. So basically, if I say in terms of incentives for interconnection, because as I told you before, that long back all the state governments in India were told to generate power and take care of their own power systems. And then later on, people started, okay, no, all these states have already established whatever they can do, and to go even ahead, then further what they do, they converted, or they connected all these states into a region. So basically in India, there are in earlier days, obviously there were less number of states, probably I think 26 or 25. Obviously during the time, the number of states have increased. So what they did, that all these states which are coming under northern part of India, they connected them in one region, and then eastern part in one region, western part in one region, southern part in another region, and the northeastern states are connected into another northeastern region. So then these regional operators were operating that. So initially states were operating their power system, then these region were operating their power system, and then eventually all these 5 regions were connected, and now the complete Indian power system is being operated by the central entity. And the central is important because we want to because power system is if there are many people who are operating power system, then it can get conflicting signals and it can create problems. So that's why it is important to work by an individual entity. Now, if I talk about the incentives for interconnection, so obviously, as I told you before, it becomes easy to operate, or rather coordinated use of power plants. So if let's say more power plants, so obviously if let's say power plant is there in eastern region and a power plant there is in the northern region, then you can easily coordinate with them and then run a power. Let's say if there is a disturbance on one side of the network, then you can tell that side of the power system to operate and manage that. So that becomes very convenient. Also, sharing of emergency services is also very important. Emergency reserves is important. Reserve is mostly whenever a contingency takes place. In that case, you need some reserve, some additional power is required. And if you have, let's say, a big system there is a lot of power plants are there, for example eastern region and northern region, if both are connected, then you have more number of power plants, and then you can easily transfer the reserve from one area to another area. So this becomes really important. Just a second. Sorry, I'm getting a call again often. Okay, just a second. This is really disturbing. Okay, sorry. Yeah, so we can share the emergency reserves, and we can have high system security, because if more generators are there, more transmission lines are there, more different loads are there, you can easily manage everything to ensure security. And especially the short circuit capacity of the lines also improves once if you have more networks connected in parallel. Obviously, if more number of generators are there, you have possibility of trading also. You can trade electricity at a cheaper price, because let's say if in northern region, let's say where I'm located in Uttarakhand, here there are a lot of hydropower plants are there, and obviously hydro is cheaper. So if let's say eastern region is connected with northern region, so cheaper power can be transferred to those regions as well. And obviously, as I told you before, the ways of coupling could be the AC coupling or the DC coupling. For example, AC is basically a synchronous connection, and DC is asynchronous, because you are converting a AC system to a DC system and then DC to AC, and there you can actually change or play with the frequencies. So for example, I can tell you India is connected with Bangladesh. India is supplying power to Bangladesh, and there we have a asynchronous DC connection in between India and Bangladesh, and then Bangladesh is taking power from us. On the other hand, India is taking power from Bhutan. Because Bhutan has a huge amount of hydropower plants, and they do not require that much power, and they sell the excess power to India at a cheaper price. Similarly, Nepal and India, again here also at times whenever Nepal has an excess, they sell power to India. Whenever they are in short, we sell power to Nepal. So it is a trade-off between India and Nepal. So this is the advantage, this is the way people connect synchronously through AC and asynchronously through DC systems. Now, lastly, I'll just close with this slide. Give me just 1 or 2 minutes. So this is the big Indian grid. Probably it is difficult to see all the connections. I tried to increase it, but you can see that this is really a huge system, and a lot of lines are there at different voltage levels. So in India, we have 132 kV, 220 kV, 400 kV, 765 kV, and 1200 kV lines, which are coming up, which is even higher voltage level. And we have around 4,26,000 circuit kilometers. So these size of kilometer of wires are already connected. This I'm talking about more than 220 kV level. Now, Indian generation or the installed capacity is more than 384 gigawatts. With thermal has the highest capacity, 234 gigawatt. Thermal includes coal, gas, and diesel. If you sum it, obviously you'll get 234 gigawatts. And then hydro as 46 gigawatt, nuclear 6 gigawatt, and renewable is 96 gigawatt. And I'm sure everybody has observed saw the news that just a second. So this is the installed capacity in India, and also you have heard that renewable India is coming up big way with renewable, and it is planned to install around more than 200 gigawatt of renewables, and you can see the size, how the way it is going to increase. With this, can you guess what is the peak demand of Indian power system? Can anybody guess? Am I audible? Yeah.
137 gigawatt.
Sorry?
137 gigawatt.
137. Yeah, means
Yeah,
no, it is actually more than
yeah,
171 gigawatt. 171 gigawatt. It is what it is somewhere around 180. But yeah, I found the number is 171 gigawatt, but it is still increasing. So you can imagine that India has already become a surplus state, surplus country. Surplus, what do I mean here? Because the power generation is more than what we require, but obviously still because of lot of issues, uh, we still face load shedding and power outages. So with this, I'll like to end the today's lecture. I hope if you have any questions you can ask me, or else we can close this. So this is just a brief introduction about the course. Any queries? If no queries, then I'll stop this lecture then.